Now, any questions before we move forward?
So I remember when I was doing some computer vision related project that the homogeneous solution is quite important to help us to solve some of the matrix. Could you explain why adding the zero row and the zero column that's going to be very helpful?
You mean the last row we added and the extra column we added?
Yes, I recall that it was very important to help to solve some of the problem in some of my previous computer vision project, but I can't remember exactly why.
No, so if you don't have that if you don't have that row and extra column, you will not be able to perform shifting operation, right? With just 2 cross 2 matrix, it will only allow you to perform scaling and rotation.
Oh, okay, I see. Yeah, that's
Okay.
fine.
I was wondering with like the 2x2 transformation and also the 3x3 by extension, does it have like issues if you're trying to do like a 90-degree rotation? So like if the point is in like the positive x and y coordinate, and then you do a 90-degree rotation, so then it's facing the positive y negative x quadrant, then will the transformation not, will the rotation still not point to the point in the positive x and y quadrant?
No, Joshua, I didn't get your question. Like, because this is when we're talking about that coordinate system, we are taking into account like which direction we are moving, right? So can you rephrase the question? It wasn't clear to me like what exactly you're trying to ask.
When you're doing the rotation, the numbers change to still point the vector to the same like endpoint. So like in the previous image you had before, there was the X and the Y, and they had like the ticks out, and they pointed to a black dot. And then when you rotated it slightly, this side. So this one, they both point to the black dot here. If you were to do a 90-degree rotation, so then it's pointing. So neither arrow is pointing in the direction of the black dot. Would the rotation still have the coordinates in the end point towards the black dot?
So you're saying instead of like this small amount of rotation, let's say we rotate this all the way up to here. So then
Yes.
this is your x-axis.
Yes.
So I mean that is fine, right? Then this point is going to be in the 4th quadrant.
Okay, so the
here.
point then moves with it when you do a rotation of 90 degrees or higher.
Yes. It will just change the quadrant. Okay.
All right. Thank you.
So any other question before we move forward?
Professor, can you again explain why the negative, why, how did the sign change when turning to the right in the rotation?
Okay, yeah, let me go to that slide. All right, so the earlier matrix which we derived, that was cos theta, and this was cos theta, right? This was negative sine theta, and this was sine theta.
Yes.
All right. So that matrix was when we are rotating the axis by angle theta towards the left.
Okay.
All right. Now, if we do that, then we'll get like this red axis.
Yes.
Right. Now, if you think about this point, now this point it is like closer to the axis, right? It's pretty close as compared to blue. So what do you think, like in which direction the point moved? It moved by angle theta towards right.
Yes.
Is that true?
Yes.
So when we are moving with an angle theta towards the left, the point is moving in the opposite direction.
Yes.
So the purpose is to move the point, not the axis.
Okay.
So therefore, if you want to move the point with the angle theta towards left,
Oh,
will have
okay.
to move the axis with angle negative theta towards right? So it's in the opposite direction. That's why we changed the sign here.
Okay, got it. Thank you.
Good. I think there's one more. Okay, question from Sanit. If anyone is having trouble with the rotation matrix, I found the derivation from polar coordinate. Yeah, that's actually pretty easy if you use polar coordinates. Okay, good. That's a good comment, Sanit. Okay. Any questions on that before we move on to next lecture?
Yes, I do. So for a single value decomposition that you mentioned that we only use a few of them, but I'm confused that if we lost some of the single values which that represent the pixel of the picture, shouldn't it turn to black? Why did it just blur?
No, so if you, okay, let me go back here. This is your original image, this matrix, and this is going to be 256 cross 256, right? And we perform the decomposition, we obtain these matrices U, sigma, and V. And
Okay.
this U, sigma, V are not the like actual pixel values. This is like some kind of decomposed format, which is telling you what is like the most prominent unit vector which can be used to represent this image.
Okay, I see. So it's
Right.
not actually losing the point of the original pixel, it's just losing the data of the decomposition.
Right, right. That's true.
And then when you like pick a single value that is less than the original, how did you pick? You only pick the first 20s or you pick the even one?
Right. So this you will have 256 different columns, right?
Yes.
And this sigma will have 256 different diagonal values. So those diagonal values will tell you which component is actually important, which is not.
Okay.
Okay, so the magnitude of those values will tell you that, and you sort those. It's actually sorted already. So you use like those values which have high magnitude and just use those components.
Okay, can you explain V a little bit more? Because U is quite like a single value, which is kind of like unique identity of the decomposition, and the sigma is the scalar. And what exactly V is doing here?
Okay, so U is telling you what's like the most what's the most prominent component, right? But how much of that component you need to reconstruct that image, right? Because you have to perform linear combination of multiple components. So this is just scaling them independently, but this is kind of linearly combining them together. So
Okay.
even to construct one column of that image, it's not just like taking one column from this and scaling it. So that's the first step. So even to obtain that column, you will have to perform a linear combination of all the columns. And the weights for that linear combination is coming from V.
So V just needs to be here, needs to be stay there in order to kind of like forming the original matrix back.
Yes, yes.
So in terms of the meaning, it doesn't really like help us to process the image. It just needs to be there mathematically.
Yeah, that's true.
So, okay, so the U is just a single value, which represent the uniquity of the matrix, and sigma is the scalar, but it's also the eigenvalue. And we can determine how important are those U elements by doing something with the value.
Not how important. Not how important. How important is indicated by the sigma. This is like what's okay. So V is telling you the recipe to reconstruct the image. So let's say you have red color, blue color. How much of red? How much of blue? Because eventually you will combine all the colors to get like something in the input image.
Okay.
Okay. So if you think about like a normal RGB image, U is giving you like red, blue, and green. Let's say you have 3 spaces, right? And sigma is telling you how much of red, how much of blue, how much of green, just scaling that. or how important is red, or how important is blue. For example, if you have image of sky, then you know blue is very important,
Right.
right? But V is telling you like to actually form that pixel value, how will you combine these three together? Because even in blue, like the shade you have, there will be some component of red, right? It will be linear combination of all R, G, and B.
Yeah, got it.
Okay. All right, good. So let me see. A question from Venkat. Can we consider V as an equation which uses U and sigma? Yeah, I mean equation, because that's kind of combining those different components together, right? And assigning different weights. Okay. All right, so I think that was the last component which I wanted to cover in linear algebra.